Try that. All right, thanks for coming. So today you came in.
Continue Pascal's talk. Yeah.
Yep. Yeah, so like Pascal a couple of weeks ago, I'll be talking about a couple of papers that we've written together with, so the first one was with Pascal and Kenichi Kowabayashi and Ojong Kwon and Zhang Yulun. And then the second one was the same set of authors, but swap out Kowabayashi for Young-Ho Yu. Okay, so I should just quickly recap some things. So the people that started this whole thing, Erdős and Pósa in 1965 showed that for every integer k, every graph has either k disjoint cycles or a set of roughly k log k vertices hitting all cycles. So in some ways, this tells us exactly what a graph looks like if it's a long way away from being a forest, if it's a large distance from a forest in terms of vertex deletion. It must contain lots of disjoint cycles, or you should be able to delete a small number of vertices and obtain a forest.
K log K is difficult? Or
That's a good question. I don't actually know what the example that shows this is tight, but you are correct. It is tight. They also showed that this was the correct order of magnitude. And this breaks down. So this is not true for odd cycles. So if you want to know what a graph looks like if it's a large distance away from being a bipartite graph, the story is different. And the reason it's different is because of what we call Escher Walls. So an Escher wall consists of a wall, which is this sort of a graph, together with some set of paths which link the top to the bottom, so that and the property is that every odd cycle of this graph must use an odd number of the red paths, and every cycle which uses exactly one red path will be odd. So with those two conditions, there do not exist two disjoint odd cycles in the Escher wall. However, if we only delete a small number of vertices, then we can, so if I try and delete just some small number of vertices, then there will be some cycle in the remaining graph, which will be odd. So something like this. And Reed showed, I think in 1999, that essentially the Escher wall is the only obstruction to a similar Erdős-Pósa result for odd cycles. So, for every integer k, every graph has either, so we have three results. So we could have k disjoint odd cycles, or some f of k vertices hitting all odd cycles, or some large Escher wall. And it's not completely a trichotomy, because you might have disjoint odd cycles as well as an Escher wall. But the Escher wall does actually guarantee that you don't have a small hitting set. So yeah, you can only have two of the three. Okay, so no, I don't. I don't. Sorry. It may be that there's a simple function that's known. Actually, wait. Is it going to be? My guess is that this is also all this, but I don't actually know. Okay, so after this, there have been various other classes of cycles where people have asked this sort of question. So I might try and draw some sort of table. Yeah.
I think towards your question, the large Escher wall plays a role there as well.
That's yeah. There's some
with two parameters.
yes. Yeah. So I don't know what there's two parameters, and I don't know what the exact relationship between them should be. But possibly Reed did know. I don't want to say that he didn't know. Okay, so there are various different ways you can look at different sets of cycles in graphs. So you could impose some lower bound on the length. You could impose some modularity constraint. Or you could require that the cycles all intersect some prescribed set of vertices, or some prescribed sets of vertices. So so if we have none of these constraints, then the Erdős-Pósa theorem is the original Erdős-Pósa theorem. If we put some lower bound on the length of the cycles, then this is also Let me find the right person to cite here. I think this was first done by Dieter and Neumann Lara. Excellent, thank you. Yep. Maybe that was 1984. So this is just cycles of length at least t for any fixed t. Of course, we have we've already looked at the odd cycles. So then we get Reid's result. So instead of a half integral, instead of the Erdős-Pósa result, we'll call this one a half integral Erdős-Pósa result. So what this means is that instead of finding a packing of disjoint cycles, we can find some set of cycles where maybe they share some vertices. So here I've drawn 3 cycles which intersect each other, but no vertex in more than 2 cycles. So if we have a collection of cycles where no vertex is in more than 2 of the cycles, we'll call this a half integral packing of cycles. And if you replace packing with half integral packing, then you do get a similar result to Erdős and Pósa, even for odd cycles. Okay, so this is with no constraints here. So then if we have one set of vertices, so we pick some set of vertices and we want to look at cycles which intersect that set of vertices. Then Kakimura and Kawarabayashi in 2011 showed, oh, yes, thank you, and Marx in 2011 showed that we still get the full Erdős-Pósa result for these cycles. And then various combinations of these have been also studied. So if you have a lower bound on the length and you prescribe a vertex set, then you still get an Erdős-Pósa property due to Brunn, Jus, and Schott. If you look at odd cycles, and you prescribe a vertex set, we can only hope for the half integral version, because the same Escher Wall construction, if you just take the entire vertex set of the graph, would be an obstruction. But we do get the half integral version. This one is, I think, without Marx. So this was the paper I was confusing it with before. But yeah, Kakimura and Kawarabayashi. Um, 2013. Oh yes, so this is again the, I'll just put a star to indicate the half integral version. Then if you have 2 prescribed vertex sets, then Kuhn, Jus, and Wallen in 2018 found the Erdős-Pósa property here. H. Is it? Wait. Thank you. Yeah, I always get this wrong, so I wrote it down. Oh yes, so that means that so suppose that I color some set of vertices blue, and I color some set of vertices red. Maybe I shouldn't have done it with this picture because I'll use it later. But I'm interested in cycles which use at least one blue vertex and at least one red vertex. So that's what that means. Yeah, the colors are allowed to intersect. That doesn't change it. And you should get the function that you get to the duality shouldn't depend on the coloring. So it should work. One function should work for every coloring. So, and it's known that here they get the full Erdős-Pósa property. If you extend to 3 prescribed vertex sets, then you can't get the full Erdős-Pósa property. And yeah, maybe I just mention one or two more. So cycles of length 0 mod m. If we don't impose any restriction on the length, then we don't prescribe any vertex sets that you need to intersect. But you take an arbitrary value m, then Thomason got the full Erdős-Pósa property, 1998, 1988. This is much earlier. So then also we have a nice recent result of Thomas and Yu that if we take cycles of L mod P, where P is a prime power, then we get, yes, this is full Erdős-Pósa. So this is Thomas and Yu. Wait, maybe odd prime power. Yes, you can't hope for yes. Yeah, that's important. Good. So this the fact that this is really looking at odd is really important. If it was at some other odd prime, then you don't get the same behavior. Okay, so this isn't a complete exhaustive list of previous results in the literature by any means, but this is a list of results that we have been able to generalize. So our results, our general theorems do imply all of these. So I'll start with, if we have some bound T, and we have any finite set of modularity constraints, and we have any finite collection of prescribed vertex sets, then we get the half integral version. So this was, so this is the first of the two papers. Yep, so this was finished last year. So this is, so no matter what constraints you put in, basically, we always get a half integral version. The most recent result that I want to talk about answers everything else. So if you're in here, we can now determine exactly when we get the full Erdős-Pósa version. But to describe the full result, I need to describe something. I need to describe the class of obstructions. So, so this will be a repeat if you saw Pascal's talk, which I think maybe everyone here did, but I'll try and go over it quickly. So given an abelian group gamma, and constants theta and kappa and some subset of allowable values in gamma, canonical obstruction consists of a wall of order theta and a collection of paths arranged we arrange the paths nicely around the boundary of the wall, and altogether we need to satisfy a few conditions. So I perhaps need to take one step back. So in this setting, every edge of the graph will be assigned an element of the group gamma. And then we'll say that the weight of a cycle is just the sum of the weights of the edges of the cycle. Okay, so the important points are that every cycle of the wall has weight 0. Actually, we say something stronger, that every path between branch vertices of the wall will have weight 0. Second point is that every cycle with value in A, so if the cycle has an allowable value, then it must intersect every let's say this is a set of paths. Every set of paths so it's important. So each of the sets of paths will be arranged in one of 3 ways. So we call this arrangement a nested set of paths. These blue paths we call a series set of paths, and these red paths we'll call a crossing set of paths. So this just refers to the arrangement of the paths around the boundary of the wall in the collection. So they should follow one of these three patterns. So what we want is that every cycle with an allowable value uses an odd number of paths from each crossing or nested set. And the reason that this is important is that otherwise maybe you could have a cycle which does something like this. And this ends up being a problem. So if it uses this thing twice, it's almost like it didn't have to use the set of paths at all.
Means that color.
Yeah, I've grouped them. So here I've drawn three different sets of paths, which.
Is it lengths?
So the length of the path isn't actually important in this setting. But so because we have group weights instead. So yeah. Also in the wall we can have subdivision vertices, which we also don't care about. Okay. So yeah, it's important that we use an odd number of paths from each crossing or nested set if we want to get a value in A. Then there's a couple more points. So every cycle which uses exactly one path from each set has value in A. And finally, we need to satisfy one of three conditions. So option one, there are at least three series sets of paths. Option two, there are at least one series and at least one non-series sets. So either crossing or nested. Or option three, there are an odd number of nested sets. Yeah. So, yeah.
Only 3 sets are possible for 3 sides of the word, or?
You can have any number of these in total. It was just easier to just draw 3 because there wasn't much room. Yeah. It's important that all of the end vertices of the paths are branch vertices of the wall. That was part of the reason that there's not much room to draw many sets of paths.
Two different sets are intersect their branch vertices?
No, they should have disjoint sets of branch vertices, and they shouldn't mix. So if you take some interval in the wall, there should be some interval which just contains the blue endpoints and no red endpoints, and some interval which just contains the yellow endpoints and no, something like this. I guess that's not quite true. You could have because the endpoints come in 2 sets, so there should be a pair of intervals which together contain all the yellow. I could in theory have another inside here. There's something else maybe, but I've forgotten. Yes, so, and also for the crossing. So there's nothing to do for the series one, but the crossing one could also be broken into 2 different sets and have something between them. But that's the only sort of mixing that you're allowed to have. But subject to those restrictions, you can have any number of these things around the boundary.
Why is all over
What's the question? Oh, sorry, an allowable value, I just mean, so this is the set of allowable values. Yeah. Oh, and I just realized so I didn't tell you what this parameter was for. This parameter should be the kappa paths in each set. Okay, so this is the description of the canonical obstructions, and with this description, I can finally state what our result actually is. So let me just clear up this board. Okay, so what we actually showed was that so for all let's say non-negative integers, so how many am I going to need? M, K, omega, and kappa, and theta. There exists some function of these parameters such that given a graph G whose edges are labeled with m abelian groups let's call them gamma 1 up to gamma m. And given omega I as a subset of gamma I with the size of the omega I bounded by this other parameter, so for all I, then either so there are three possibilities now. So either G contains k disjoint cycles with so let's say whose values avoid omega I for all I. So this is one set of cycles which where for every I, the ith value of the cycle is not in the set omega I. So that's one possibility. Or the second possibility is that G contains a hitting set for these cycles of size at most this function mk omega kappa and theta. Or the third possibility is that G contains a canonical obstruction for some subsets of the group labelings. Where we take the group to be the product group over the subsets, and we take A to be the set of values such that none of the coordinates of the value are in any of the obstruction sets of gamma omega I. So
S is just all the integer compound.
so S is so for some subset S, of the group labeling. So S is a subset, yeah, a subset of the integers from 1 to n is what it should really be. And now so the extra parameters that I haven't mentioned here are the parameters for the canonical obstruction up there. And there's one more additionally. This obstruction contains a half-integral packing of kappa allowable cycles. And this is allowable in the original sense of this condition. So, in both of these two conditions, we actually get the half-integral packing, because the integral packing, the packing of disjoint cycles is an example of a half-integral packing. So this does imply the half-integral Erdős-Pósa result. But in many cases, this also implies the full Erdős-Pósa result. And to see why that's true, you need to look very carefully at what's actually going on with the obstructions. That's what I was hoping to have some time to do.
Obstruction looks a little bit different than what you had earlier for just odds side.
Oh yes, so this, well, it does look a bit different, but if you imagine that if you imagine that the size of each of these sets is very, very large, and the wall is very, very large, then actually this, if you rub out this blue and this yellow, then it actually is the same picture. It's just with some extra stuff. That's not maybe immediately obvious, but they're sort of, one contains the other. There really isn't any fundamental difference between those pictures. Yeah, so I suppose maybe I will try and give an example of some results that we can derive from this. So let's see. Let's see. So cycles of length at least 6 and of length congruent to 1 mod 5 and intersecting a prescribed set S satisfy Erdős-Pósa. Okay, so here's an example of what our theorem can show. And the reason that we can show this is because so we can encode these cycles with group labelings, first of all. So let's just let the first group labeling be a labeling with the integers. And we're going to forbid all of the small positive integers. Then we're going to let the second group labeling be with the integers modulo 5, and we're going to forbid values 0, 2, 3, 4. That's all of them. And then the third is another labeling with the integers, and here we're just going to forbid the value 0. Okay. So given a graph now, let's say that I have some prescribed set of vertices, just these two here. Then I'm going to assign, for the first two group labelings, I'm going to give each edge the value 1, 1. But for the third group labeling, I'll give the edge value 1 if it's incident to the red, and value 0 if it's not incident to any red vertex. So I have some labeling like this, and with this labeling, so if the length is less than, or if you have a cycle whose length is less than 6, then the value of the first coordinate will be one of these 5 integers. Because you just add up the first coordinate of all of the edges of the cycle, and you'll get at most 5 unless the length is more than 5. Similarly, if you have a cycle whose length is not congruent to 1 mod 5, then in the second coordinate, you will obtain a value which is not congruent to 1 mod 5, and you'll land in this set. And finally, if you have a cycle which doesn't contain a red vertex, then the cycle will have value 0 in the third coordinate. So in that sense, this really does encode the cycles that we care about in this setting. So if we look at our main theorem, we should have some function which allows us to obtain one of these 3 different results. So, and what we want to find is that we actually obtain one of the first 2 results. But to see why that should happen, we need to look at exactly what the third option would mean. So, okay. So, for a set of, so for a canonical obstruction, so firstly, note that we need to find a wall inside the graph, and every cycle in that wall has to have weight 0 with respect to this group that we take. Well, if we look at our group labeling that we've defined, you'll notice that we can't possibly have a wall where every cycle has weight 0 in the first coordinate, because no edge, so every edge has weight 1 in the first coordinate. So every cycle will actually have positive weight in the first coordinate. But that's fine, because the third condition, so this is why it's important that we are allowed to take a subset of the coordinates. Okay, so we need to throw away the first coordinate, but now maybe we can still obtain the obstruction. Okay, and all of these conditions now sort of work out okay, except we have this interesting restriction here. So we know that whenever we take a cycle which includes exactly one part from each set, we have an allowable value. But then the second restriction says that we are forced to take an even number of paths with respect to any set which is crossing or nested. But the thing about this,
So,
yeah?
It means nothing.
So sorry, in this case, so A was meant to be allowable. The omega sets are the non-allowable values. So here we have gamma equals, say, just Z5 cross Z. And so allowable means that you have some values G1, G2, such that G1 equals 1 and G2 is not equal 0. That's the set of allowable values. But the point with this set is that if C is allowable, yeah?
Sorry.
Yeah.
Every allowable cycle intersects every set of paths, and every allowable cycle intersects every path odd number of times. If it's crossing the nested.
Yes, that's right. It must, yes. So what we actually find in this case is that it's impossible for there to be a crossing or nested set. And the reason for that is that if the value of some cycle C is allowable, then actually, let me just think for a second. Actually, 6 times C is allowable. Because 6 is congruent to 1 mod 5. So you can't, and of course 6 times x is not equal to 0 unless x equals 0. So in this case, if G1, G2 is in A, then 6 times G1, G2 is in A.
Can I look first also behind the back of the first book?
Back to this one?
Yeah.
Yep.
So that Z from gamma 3 or that is from gamma 3 or gamma 1? Gamma 3?
So yeah, because we had to rule out gamma 1 because no cycle has weight 0 in gamma 1. But we require that every cycle of the wall has weight 0 with the, yeah. So this is why we have to rule out we have to rule out the first coordinate. But if we keep either of the second coordinates, we still can't have a nested or crossing cycle, a nested or crossing set of paths, because it won't satisfy this condition that you have to take an odd number. Because we see that we can always take 6 things from every, we can always take 6 paths from every set to obtain an allowable value. This is maybe making some assumptions.
Where's 6C here?
So if you have some, so that's just is meant to indicate that if you have some cycle whose value is allowable, then you could take 6 copies of that cycle and add them together, and the value would still be allowable. So just if you just multiply the group values by 6, I guess. But yeah. So I guess there is some. This is actually a slight lie. How I worded this here. So what we actually say here is that whenever you let's see. So given paths let's see. Maybe I'll just say in words. So what we actually find is that stronger than this condition that you need to take an even number of paths from each set. If you imagine taking a collection of paths and having a set of integer coefficients for those paths, such that the group values of those paths multiplied by those integer coefficients and then summed up, then the total of all of the coefficients of each nested, so if the end result is allowable, then the sum of the coefficients of the paths from any nested or crossing set will be odd.
Now you can just put.
So now I can say something like this without it being complete nonsense. Yeah. So I forgot that was actually important for this part of the proof. But because I think at some point we were talking about wording the conclusion more like this, and then we realized that we had to word it in a more technical way. But yeah, I forgot why that was for a second. So given that, we can actually say that now, since 6 multiplied by any cycle that's allowable will still be allowable, that forbids us from taking any crossing or nested linkage. But then we only have one condition. There's only one. That means condition 1 must be satisfied. But what we also find is that if let's say if G1 plus G2 plus G3 is an element of A, then Gi times Gj So we should be able to pick two, whenever we have three elements which sum to a value in A, we should be able to just pick two of them such that they generate a value in A. So this is so basically this is not too difficult to show. If G1, G2, and G3 generate an allowable value, then at least one of these three, so without loss of generality, G1, so the first coordinate of G1 is non-zero. Because if all three values have 0, then the sum can't possibly be non-zero in the first coordinate. And similarly, without loss of generality, G2 equals A prime B prime, where B, so this isn't quite true actually, where B is non-zero, B prime is non-zero. But if, so now what we do, so maybe I'll just say GI here, where I is allowed to equal 1. So then it's true. Now how do we do this? So there exists some integer k such that k times A is congruent to 1.5. Just because 5 is prime. And then there exists some integer L such that k times G1 plus L times 5 times L times G2 is an element of A. So what this means is that if there are three sets of paths which are sufficient to give us a value which is in A, then what we could do is we could throw away one of the sets of paths and take many copies of a path from these two sets.
Series.
Sorry, we should have them all in series. So we could replace all the paths in some thing which is contributing this G3 with just a large set of paths from the first two to obtain an allowable value. But this contradicts one of the points. And again, I think I've slightly lied about the statement of the point. There's this point here that every cycle with a value in A must intersect every set of paths. So what we actually find is that we have some redundancy, and that means that the construction actually can't exist. Yeah. So yeah. In this particular case, well, I guess L can be either 0 or 1, basically, depending on what the first. So because there's only one restriction, we only care, and actually in this particular case, L can be 1. That's true. In this particular case,
This is the general method we use.
But yeah, there's some, this method generalizes and we can make this sort of results in a bunch of cases. Yeah, I think I should stop here. So sorry for going over the time. I'm sorry I didn't get to all of the things that I said I would get to. But yeah, thank you.
Thank you.
Christian?
Is there algorithms that can check whether there exists an obstruction or not?
Does our proof imply any algorithm, do you think? Decidable, sure. But I guess it's.
The algorithm will produce one of the three outcomes, right?
I don't know with general abelian groups if there could be some problem. Do we? I think probably the answer is yes, but we don't. So we don't really focus on the algorithmic side there. So it wouldn't be, and it wouldn't be any sort of efficient algorithm that we would get. The bounds for the so this function that we get, this is not a nice function. This is a very not nice function that we get. It's mainly we're just interested in the existence. So yeah, I think at least most of the steps could be translated to some algorithm, but I'm not sure in general.
Is there any possible structure other than the cycle which satisfy Erdős-Pósa?
Yeah, actually. So people have looked at. So there's a nice result about if you want to find, instead of a cycle, you consider a subgraph which contains a particular graph as a minor. So and you want to find a packing of these subgraphs which contain a particular graph as a minor, or you want to find a heading set so that once you delete it, the entire graph doesn't contain the particular graph as a minor. And in this setting, it's actually known that the Erdős-Pósa property holds if and only if the graph is planar. And there's quite a nice proof that it fails for non-planar graphs. Because what you can do, if I have you pick the smallest surface on which the graph embeds, say. So maybe I've got a graph like this embedded on the torus. And all you do is you draw many disjoint copies of this graph. Now, of course, when you draw them, the edges are going to cross each other. So as soon as I draw two copies, I'm going to get edges of the first copy crossing the edges of the second copy. So in order to get rid of this problem, I just add some extra subdivision vertices at all of the crossing points. And I do this many times so that that every point is only in two of the copies. Now, this gives me a half-integral packing of graphs which contain the particular graph that I started with as a minor. So each of the yellow contains this grid that I drew as a minor, and the white contains the grid that I drew as a minor. But the thing to notice is that we can't have two disjoint copies of the graph as a minor because the genus of the surface is not big enough. So if you delete any minor, any graph which contains this as a minor, you will, all of the components of the graph will be planar, or the remaining graph will be planar. So if the original graph isn't planar, this allows us to build a graph which does not contain two disjoint copies of that graph as a minor, but the smallest hitting set must contain at least one vertex for every pair of at least half as many vertices as the number of copies that we drew. So people do look at things which are not cycles here, and this has been generalized a bit, and I've looked at if you prescribe a vertex set, or you give so this has also been generalized to some degree. Yeah.
No, I think that's